Hello everyone. In this video we will continue the atomic structure and periodicity worksheet chemistry AP level. Number 35, which of the following is expected to have the smallest radius? As we know that the atomic radius increases down the group but decreases across the period. The options given to me contain potassium and calcium. So I want to find the smallest one, so I will put in my mind that potassium is not an option. So directly I eliminate this from my options. I am left with calcium as calcium 2+. Calcium atomic number 20, and because it's atom, it has 20 electrons. Calcium 2+, because it's ion, monoatomic ion, it has 18 electrons. Both of them, they have the same atomic number, but number of electrons in Ca2+ less than that of the calcium atom, which make it having the smallest radius. So the option is C. Number 36, compare the following elements with respect to the characteristics listed below. We have sodium, boron, aluminium, and carbon. Which has the largest atomic radius? Let us check in the periodic table. We have sodium. We are talking about sodium, boron, aluminium, and carbon. We need to find the largest atomic radius. As we said, going down the group, radius increases, while across the period it decreases. So this leaves me with the option A, which is the sodium. Which has the most electronegative affinity? Electron affinity, it's when the energy is released upon the addition of electron to isolated gaseous atom. Electron affinity increases across the period but decreases down the group. So increases across the period electron affinity. So between sodium, boron, carbon, and decreases down the group. So C is the best option. Which has the largest ionization energy? Ionization energy, like electron affinity, increases across the period and decreases down the group. So, C, carbon, carbon, which means part D, the option. So also here, part D is the option. In number 37, compare the properties of the two elements. Which element above is a metal? We know that the metals constitute the left-hand side of the periodic table. These are metals. And the right-hand side of the periodic table, non-metals. So this is the S block. And here we have P block. So the electron configuration that ends with S is in the left-hand side, which is metal, so option A. Which element would have the lowest electron negativity? The electron negativity increases across the period and decreases down the group. So the one which has the lowest is the one to the left, which is A. Which would have the larger first ionization energy? Larger will be across the period, as we said, so it will be part B, or option B. Now AP free response questions, let us solve for them and answer the following problems about gases. The average atomic mass of naturally occurring neon is 20.18 atomic mass units. So this is average atomic mass. There are two common isotopes of naturally occurring neon as indicated in this table. Using the information above, calculate the percentage of the percent abundance for each isotope. I'm gonna assume the percent abundance for neon 20x, the percent abundance for neon 22y, and I will construct equations. The first equation I can write, average atomic mass is the percentage abundance of neon 20 times its mass 19.99 plus the percent abundance of neon, 22 times 21.99, all divided by 100. Average atomic mass given 20.18. I will multiply it by 100 equal 19.99x plus 21.99y. And this is the first equation that I construct. I have to construct another equations to solve for the two unknowns x and y. The other equation is that the summation of both percentage abundance equal to 100. This is the second equation. Upon substituting 2 in 1 and calculating, we will find y equal 8, while x, the percent abundance for neon 20, is 92%. So this will be 92% and this will be 8%. Now calculate the number of neon 22 atoms in 12.55 gram. This is the mass of naturally occurring neon. First of all, let me find the number of moles and then I will relate it to atoms. It's the mass over the molar mass, which is 12.55. The molar mass for neon 22 is 21.99, which is 0.5707 moles. Now I will change the moles into atoms. 0.5707 moles. I will multiply, and we know that every 1 mole of atom corresponds to Avogadro number of atoms. So the answer will be 3.437 times 10 to the power 23 atoms. Part B, a major line in the emission spectrum of neon corresponds to the frequency 4.34 times 10 to the power 14 second minus 1. Calculate the wavelength in nanometer. We want to find the wavelength. So lambda equals c over frequency nu. C, it's the speed of light. 3 times 10 to the power 8 over the frequency, which is 4.34 times 10 to the power 14. The answer 6.91 times 10 to the power 3 meter. Let me change it to nanometer as it is required from the problem. So it is times 10 to the power 9 nanometer over 1 meter, and the final answer is up to 3 significant figures, 6.91 times 10 to the power 12 nanometer. In the upper atmosphere, part C, ozone molecules decompose as they absorb ultraviolet radiation, as shown by this equation. Ozone serves to block harmful ultraviolet radiation that comes from the sun. A molecule of ozone absorbs a photon with a frequency 1 times 10 to the power 15. So this is the frequency of the photon that one molecule of ozone absorbs. How much energy does the ozone molecule absorb per photon? Let us calculate using the formula, and E equal h nu. H, which is Planck's constant, 6.626 times 10 negative 34 joule times second times the frequency 1 times 10 to the power 15 second minus 1, and the answer for the energy 6.626 up to 4 significant figures times 10 negative 19 joule for every how much energy in joules does the photon or molecule photon. Now, the minimum energy needed to break an average oxygen bond is 387 kilojoule per mole. Does a photon with a frequency of 1 times 10 to the power 15 have enough energy? Definitely, to see if it has enough energy, we have to find the energy in joule per photon and then compare it to the one in part I. the energy, the E minimum, bond energy, 387 kilojoule per mole. Let me change it into joule per photon. Kilojoule, every 1 kilojoule corresponds to 1000 joule, and then every 1 mole photon corresponds to Avogadro number of photons. Mole cancelled, and the final answer is up to 4 significant figures, 6.425 times 10 negative 19 joule. Let me compare E minimum to the E absorbed per photon. We see that the E absorbed by photon is greater than the minimum energy. So E for the photon greater than minimum energy. So the answer is yes, it can. Now, we want to account for each of the following observations in terms of atomic theory or quantum theory. Why the atomic size decreases from Na to Cl. In the periodic table, this one, we see that Na period 3 and Cl also period 3. But across the period, we said that the atomic radii decreases. Let us see why. Okay, I'm gonna make electron configuration and look at the electron configuration, and we will account for this. Na had atomic number 11, so 1s2, 2s2, 2p6, 3s1. Chlorine atomic number 17, 1s2, 2s2, 2p6, 3s2, 3p5. So across the periodic table from Na to Cl, the number of electrons in the s and p orbitals of the valence shell increases, as you see. So here in sodium, no p orbital, but in chlorine we have p orbital here. Also, the number of protons in the nucleus increases, so from 11 to 17. So the added electrons only partially shield the added protons. So it results in an increased effective nuclear charge. So here, because the atomic number, nuclear charge more than 11, so it will attract the electrons towards it more, which makes the atomic size decreases. So let us write the answer. Across the periodic table from Na to Cl, the number of electrons in s and p orbitals of the valence shell, definitely I'm talking about the valence shell, increases, as does the number of protons in the nucleus. And the added electrons, as we said, only partially shield the added protons. The added electrons only partially shield the added protons, resulting in an increased effective nuclear charge. This results in a greater attraction for the electrons, drawing them closer to the nucleus. to the nucleus, making the atom smaller, making the atom smaller. So it's because of the effect of a nuclear charge that draws the electrons closer to the nucleus. Let us account for that the first ionization energy of potassium is less than that of sodium. As you see here in the periodic table, potassium and sodium. Potassium is in a higher energy level, while the first ionization is less. Okay, we know the trend that going down the group, the ionization energy decreases, but let us see why. Let us do the electron configuration. Potassium, 19, 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. Let us do it for sodium, 11, 1s2, 2s2, 2p6, 3s1. As you see, both Na and potassium, they have S1 valence shell. Yes, both of them, they have S1 valence shell. But as you see in potassium, the principal quantum number higher than that in sodium, which makes this electron farther away from the nucleus. And if it is farther away from the nucleus, it doesn't require a lot of energy. That wise, it accounts for that the first energy is less than that of sodium. Let us write the answer for part B. Both Na and potassium have an S1 valence electron configuration. But the potassium atom valence electron has a higher N quantum number, which is the principal energy level. Placing it farther from the nucleus. Farther from the nucleus than the sodium atom valence electron. And the greater distance results in less attraction to the nucleus. Hence, less energy is needed to remove the electron. Okay, now let us see part C. We have to account why each element displays a unique gas phase emission spectrum. When we spoke about emission spectrum, we said that the lines of emission spectrum differs from one element to another element. Why? It's because actually of the unique nuclear charge and electron configuration for each element, which makes it unique, that gives unique lines of spectrum. So part C, each element has a unique set of quantized energy states for its electrons, as we said. Why? Because each element has unique nuclear charge and electron configuration. because of its unique nuclear charge and electron configuration. In reality, as the electron from the element absorb energy, they change to higher energy states. We say it's excited. Absorbs energy, they got excited. They got excited. And during de-excitation, energy is released. The opposite process, energy is released as electromagnetic radiation. Electromagnetic radiation. So each proton is associated with a specific, and each proton associated with a specific wavelength. Each proton of the electromagnetic radiation is associated with a specific wavelength, lambda, which is a flux of which produces the lines of the spectrum, emission spectrum.